Hi, this is Lori, and this is my homework for Paul McWhorter's Pico W class, lesson number 5, reading analog voltages using a potentiometer. I used to post homeworks under my Lori's Robots YouTube channel where I post my own original projects, and I decided to go ahead and separate my homework videos from my original project videos. So I'll be posting homework under Lori's Homework YouTube channel. In this episode, Paul taught us how to scale our potentiometer readings, which go between 0 and 65,000 or so, and how to rescale them into any range that we wish. And we use two equations from algebra, the slope equation for a line and the point slope equation for the line. And the key thing to being able to figure out how to do this rescaling is having 2 points on the line we want to use for the conversion. So x1, y1, x2, y2. Now for a potentiometer, we know that on the low end, for me, my potentiometer reads around 400 on the low end, and it goes all the way up to 65, 535 on the high end. So I have x1 and x2. And then depending on what kind of scale I want to go into, I'll usually have an idea of what the minimum value for that scale will be and what the maximum value for that scale will be. And that'll give me my y1 and y2. If we use these two equations and put them together, putting the slope inside here for that, the slope there, using these 2 points, the y1, x1, y2, x2, putting them in here, we can eventually turn this into a nice equation where we can take our potentiometer value and turn it into a y value. And this just shows doing it where we want to rescale our potentiometer into the voltage from 0 to 3.3 volts. And Paul showed us how to do this in the class, and here's the equation that we would come up with for that. So that's very useful. It's good to work through by hand. Eventually, as you'll see in the code that I put together, I wrote a function to do this calculation. But for the homework, Paul wanted to flip it up a little bit for us, and he asked us to do a scale where on the low end of our potentiometer we read 100, and on the high end of the potentiometer we read a 0. And that's going to end up giving us a negative slope, as you can see in the graph. And here's how that would look. And so there's our 2 points. At the low end, 400, I'm going to read a 100, and at the high end, I'm going to read a 0. And I'll get this equation. Let's go see how this works out in code. Here's the first program I wrote to just do a very simple read of the potentiometer. Set up my modules. Went ahead and set up the potentiometer on the analog to digital converter, pin 28. And here's that function I put together to transform the x scale into the y scale, and using that 2-point idea. So just calculate the slope and then put that into the second equation and return that scaled value. So pretty simple equation to put together, and makes it easy to use. Then we're going to read the potentiometer. We're going to calculate the voltage. So I'm using the voltage scale. I'm just kind of showing how to use this scale function here. I read from 0 to over 65,000 on my potentiometer, and then with voltage it would go from 0 to 3.3 volts. So that's the voltage scale, but I could also do the homework scale. And you can see it's sort of the same thing, except for now on the low end I want to get 100, and on the high end I want to get a 0. So this should work. Let's see it go. And every second it's going to give me a reading. So I've got it turned towards the high end because we're getting high volts. If I turn it down slowly, here you should see my circuit. Coming through, and I think Paul said make sure around halfway, so I'm just about halfway here, and we can see I'm almost reading about 50. And if I take it all the way down, I get 100. But you can see one thing that is kind of a little annoying is that I'm getting some negative numbers for the voltage, and we know voltage can't be negative. The other thing I've noticed with potentiometers is they seem to have a lot of noise in them. So I might try to fix that in version 2. And let's look at version 2. Very similar. Got my scale function, but I went ahead and wrote another function to read the potentiometer, but to actually calculate an average value. So with this function I put together, we can ask for an average of any number of numbers we want. So you can pick the n, 5, 10, 15, 20, whatever you like, and they give it the name of the potentiometer where you set it up on the pin. And this goes through and calculates the average and returns that. Now there's some sleep in here to try to make sure we really catch some of the variability, but the more sleep you put in here, the longer it takes to get a value back from it, so you have to be a little bit careful when you use it. Then our while true loop is pretty similar, but we're now going to use the new read pot function, and I'm going to do an average of 10. And just going to do the same calculations as we did before, except for I'm going to try to fix up where we get negative voltages. I'm just going to set the voltage to 0. Now I'm going to sleep 2 seconds to give enough time for the average to be calculated, reading it. So let's let that one run. There we go, and we're on the low end this time, so go ahead and turn it to maybe about halfway. Now it's only going to read every 2 seconds, so it takes just a little bit of time. So almost halfway, and we'll go all the way up to the high end. And yep, we're reading 0 on the high end and almost 3.3 volts. And I'll just whip it right back down to the low end, and we'll notice that for the voltage we should only get zeros, even though before we were getting some negative numbers. So you can use some of those if statements to help us not get numbers that don't make any sense. That's what I did in the coding. I have one more little thing to share, and if you're maybe a beginner, what I'm going to share after this is just some musings I've had about the way the potentiometer is read. What I love about Paul's course is he always gets me thinking about what's going on, and it was really bothering me that I've read about the analog to digital converter in the Pico being 12-bit, which means we should be returned a value between 0 and 4095. And we're reading it with this function that turns it into a 16-bit value from 0 to over 65,000. And so I started looking into that. I'm like, well, maybe there's a read U12 instead of a U16 that we could use and get it in the original format that the ADC is sending. And as much as I looked around, I didn't find a lot to help me. But I did find a nice discussion on a Raspberry Pi forum with somebody asking a very similar question. So what's up with this 16-bit, and how does it get changed from this 12-bit that comes out of the analog to digital converter into this 16-bit? And it's using a Taylor series expansion. And if it's been a long time since you took math, and even though I was originally a math major, it's been a while since I've messed around with those. But here's sort of the details, pretty complicated, but it kind of tells you that one of the things I always remembered was you can use a Taylor series expansion to approximate any function, and that's kind of what it was all about. So that makes some sense of how it's doing this conversion. But this one person in this forum was pretty tenacious and really wanted to understand what was happening here. And somebody actually took and put this on the screen in text to show how the 12-bit number is converted into a 16-bit number. And what happens is you take these the binary version of it, you take these first 4 A, B, C, D, and they get put on the end to create a 16-bit number. And I said, okay, that's interesting. So I was thinking about it. Halfway for a 12-bit number would be 2048. So it's pretty easy, right? It's the 1 at the start and then all zeros after that. And halfway between for a 16-bit, which would be a 1, and then, all these zeros would give us 32,768 in decimal. And I was curious to see what would return if we did this sort of conversion. And the nice thing is the calculator on my Mac actually has this programmer view, and it actually will let you put in decimal form numbers and then show you the binary part of that. It's really, I wish I had seen this much sooner. So for example, those of us who did the binary counter, if we put in, say, 15, we'll see that it comes out 11111 here in where it's showing the binary. So pretty nice tool for kind of going back and forth between decimal and binary and get your mind set for that. So if I want to put in the number that I would get if I were to convert this using this format for halfway, well, it says I would put a 1 here, and then I would copy these and put them over here. So then there'd be another 1 here. And I would get 32,776 for the halfway. So you can see it's not perfectly aligned, but I did find that kind of interesting about how it does this extension into the 16-bit. So maybe some of you guys know a little bit more about this. I still don't fully appreciate how a Taylor expansion is being used here in binary. That's kind of beyond my mind at this point. But I did think this was pretty interesting about how the 12-bit is being kind of scaled into the 16-bit. And the other interesting thing was, why? I was wondering, why is it like this? And it did say, and I've seen this in a couple different places, that to make MicroPython portable among various boards, and all these boards often have different resolutions for the analog to digital converter, that they went ahead and did a 16-bit read function so that they could handle any of them. And then they just scale the value that comes out of the board's ADC to a 16-bit, no matter what board it is. So I thought that was an interesting little tidbit as well. Well, I really enjoyed the homework this week, Paul. Thanks for the great lesson.